Thank you, organizers, for the invitation. So my topic is four-dimensional topology. And so I'm going to talk about combinatorial approach to construction of invariance of four manifolds. But of course, I will not go all the way, so which is the ultimate goal to end up with invariance. But I will speak just a little piece. The very first step in this construction. And the Pachner moves are just algebraic underlying setting for construction of those invariants. If we can make an analogy, then the analogy would be correct to compare them with knot diagrams and Reidemeister moves. So we build up diagrams using crossings, and then we establish equivalence of different diagrams which correspond to equivalent topological knots by using Reidemeister moves. So in triangulated setting, we have simplices depending on the dimension of the of the manifold you are studying, and then we have Pachner moves. So you compose manifolds in terms of simplices, like Tang today did compose surfaces by using triangles. This is the situation in 2 dimensions. And then the equivalence relation is achieved by using Pachner moves. So I'm not going to explain in general what is a Pachner move. So let me just start with a formal definition of the algebraic identity which realizes the principal Pachner move in 4 dimensions. Principle in the sense that if we compare with Reidemeister moves, we have 3 types of Reidemeister move, 1, 2, 3, but everybody is agreed that type 3 is the most important because the others are easier in a sense to realize. So similarly in dimension, in d dimensions, so we have a list of Pachner moves which correspond to splitting the integer d plus 2 into a sum of 2 integers. So in dimension 4, so d equal to 4 plus 2 is 6. So we have to consider different splittings of 6 into a sum of 2 positive integers. So we have 1 plus 5, 2 plus 4, and 3 plus 3. And the most symmetric splitting corresponds to most important move. And so the most important move in 4 dimensions is 3 Pachner move, which relates a 4-ball triangulated into 4 simplices to another triangulated ball split it into 4 simplices in different ways. Okay, so let me start just by defining this 3 Pachner move. So this is the 3. So let me start with let n be a positive integer and n state 3 Pachner move. A Pachner relation is the following algebraic relation or system is the following system of system of algebraic relations. And I will draw a picture, but then I will translate this picture into a formula. So the picture is the following. So we start drawing a hexagon. And we draw another hexagon. And then we draw a triangle inside each hexagon. And the first triangle, I draw it like this. Second triangle, I draw like this. Then I put, then I draw 3 vertices of triangle to 3 closest vertices of the hexagon, like this. And do similarly here. Next thing, I put arrows on the sides, all edges. So in the following way. So in the first stage, I put just consecutive arrows on the upper half of the hexagon. But on the lower half, I try to follow just symmetrically. But in the middle, I swap 1 arrow and finish as I would intend to. Then I do likewise on the right-hand side. And next, we put arrows on the triangle, but we follow the following rule. So, as you may notice, we created 6 pentagons altogether in the 2 sides. And the pentagon has an odd number of sides, and we would like to alternate the orientations on the sides of the pentagon, but we cannot do that because the number is odd, so at least 2 sides will be oriented the same way consecutively. So we will live with that, but the other edges we will try to alternate. And you can identify 1 pentagon already with 2 consecutive arrows, so the rest I will just alternate. So I put like this, I put like this, I put like this, and like this. Okay, so I just alternate, but of course I have a pair of 2 consecutive arrows. So here I also have 2 consecutive arrows. Here already I have an alternation, so I put here like this, like this. And finally, here I have already 4 edges which are oriented in an alternating manner. And so I have an 2 options here, but I choose the one which gives a clockwise consecutive pair of arrows. Okay, that's the end of the story. So I do likewise here. So here I have a consecutive arrow. So the rest I alternate like this. Here I have already consecutive. I alternate the rest. And finally, again, I have 2 options here, so I choose the one which gives clockwise. So that's all orientations, and now I just color all edges by letters, like I, J, K, L, M, N, P, Q, R, S, T, U. And so the boundary edges I am going to color the same way on the right-hand side. I, J, K, L, M, N. Now I'm going to identify these two triangles, and I'm going to identify them just in the opposite order. So this edge is opposite to this edge, so I put Q here, I put P here, and I put R here. And I have still 3 edges remaining, so I can put it this S prime, this is U prime, and T prime. And I put a sum of internal edges. So S, T, U, sum of S prime, T prime, U prime, and I put equality. And now that's the relation. And where everything is composed of pentagons, with this kind of orientation, our 2 edges go consecutively in the clockwise way, the rest is alternating. And now I just start from the first edge and then I go around. I put indices I, J, K, L, M. And this is a notation for some Q with I, K, M, J, L. So, so the arrangement of indices is like this. I start from here, which is a distinguished edge, and then I go around, but first I put upper arrow, upper index, lower index, upper index, lower index, upper index. So that's, and these are just some numbers in the ground field. So if we have an edge shared by two pentagons, that means that you put the same edge for each pentagon and you take a product. So in other words, the relation star is equivalent to sum over STU Q, and we can write I S P T J, right? This is for the first pentagon, and then I can go here, Q S L M U R. U R. Sorry? Yes? Yeah. So they are from 1 to n. Okay, so it's an end state. Yeah, thank you. So all so I, J, K, and so on all belong to 1 to n. Okay, so the index set. Yeah, so let us finish at least the right-hand side. Q, T, Q, U, N, K. Right, and I think it's clear what is in the right-hand side. You just say. So that's a relation. That's a relation, and you may ask where it comes from and what is useful for. And the claim is that there is a four-dimensional content in this relation. It doesn't come just from nowhere. It is a result of interpretation of the Pachner relation in terms of triangulations. And maybe I should just say a few words about that interpretation. So interpretation. Okay, let me just make a few remarks. So the system is highly overdetermined. Right? If we count the number of unknowns, so we have n power 5 unknowns. Just the number of components of Q, I, J, K, L, M. Each index takes n values, so we have n power 5 unknowns. Now if you count the number of equations, it is n to the power number of boundary edges of the picture. So we have the n power 9 equations. So it is a homogeneous of order 3 system of algebraic equations on the unknowns qij, kl. And so a priori, if we would choose just a system ad hoc with that number of variables and equations, it's with very low probability there would be a solution, except for 0. And so the purpose of my talk is to explain that this system is pretty much consistent and admits solutions. Okay, now let me just give an interpretation.
Why the equations number is n? What's the number of equations is n?
Yeah, so you see outer indices are fixed, right? I don't sum over them. I just color them and keep them fixed. And for each choice of that coloring of the boundary edges, we have an equality. So it gives a scalar equation. And now you just count. We have 6 sides outside, and you have 3 sides inside. So 6 plus 3, you have 9 edges on the boundary. And each boundary, each edge is colored by n possible colors. So n to the power 9. Interpretation. In terms of ordered triangulations in 4D. Yeah, and so with this remark, in principle, one can try to classify solutions for 2 states. For example, it's not a big deal. You have 32 unknowns and 512 equations. Yes?
So in your orientation, they are able to make this definition as notation for Q well-defined?
Yes, yes. So without, to avoid any ambiguity in writing. Because to memorize the arrangement of indices is a nightmare. I'm not able to do that. But as you have just seen, it's relatively easy to restore the picture.
So when paradigm is equal to 2, did you try to do broken bases?
No, I didn't try to do any numerical analysis. No, on computer, so it's open.
Q equal to 1, what's the solution?
For n equal 1?
It's homogeneous.
1. Yes. There is one solution. Q equal 1.
What is 0?
0, you mean 0. Q equals 0. Yeah, 0 may be not interesting. 1 may be more interesting.
But the system is homogeneous.
Yeah.
So you always get
0 and 1, right. So for n equal 1, there are 2 solutions. Okay, so maybe that was the first remark. Maybe second remark will be useful to make it. So we can define R with index k, and the rest I interpret as a matrix elements ij, mn, to be just q, I, J, K, Mn. Just let us introduce objects denoted R with one single K. But we interpret the 4 remaining indices as a matrix indices of a linear map or of an n-dimensional vector space tensor with itself to itself. So Rk interpret Rk as a Kn tensor Kn to itself. Right? We just Rk acting on I m tensor En gives Rk m n ij ej sum of ij. So we define such a map. Then so let me call this three Pachner relation. Then three Pachner relation is equivalent to R12, R13, R23, IJK equal R23, R12, MN, NN, Q, I, J, K, Mn, sum over Mn. And here I'm using just the standard notation for indicating for the rule of interpreting the linear map R in the triple tensor product of K to N. So this relation is written in the vector space K to N power 3. And R12 acts as R in the first two components, 13 acts as R in the first and third component, and so on. And Q remains to be scalar coefficients, and so you have we can write our identity, this identity, in this way. So you see it is still trilinear because R is nothing as else but Q in the new notation. And we have one more Q which is written explicitly. But the usefulness of this writing is the fact that if you ignore those indices and Q, you will, at least some of you will recognize the pentagon identity which realizes 3-2 Pachner move in 3 dimensions. And in this sense, so this relation categorifies the pentagon identity in the sense that the pentagon identity is not true anymore, but it is true up to some explicitly written transformation. So it's exactly in the spirit of categorization idea. If you had equality, then after categorizing, you don't have equality, but you have equivalence. Okay, now let me turn again. That's interpretation in terms of 4D. So let me just give an explanation how you can derive this identity just from first principles just by using nothing else but triangulations. So so let us start from the notion of ordered combinatorial and simplex. So what is it? This is just a power set But we can just implicitly, we should think always, we should think about power set, but in reality we can think of an ordered, linearly ordered. Linearly ordered set S of cardinality n plus 1. And that's the notion. And the standard ordered combinatorial and simplex corresponds to S given by n in square brackets, which is just a set of integers from 0, 1 up to n. And of course, I imply the linear order on those numbers. And then we have a phase maps, which, or maybe not maps, but facets of S. Okay, let me first remark that. So any ordered combinatorial and simplex has a canonical order preserving map bijection little s, which goes from standard simplex to simplex S. So it's clear, right? So S of n is S of 0, S of 1, S of n. So just a linear order. So it is we can think of any simplex as an image of that simplex just by relabeling the points. And then we have a facets of S given by n plus 1, n minus 1 simplices. Simplices di S given by S minus S of I. Right, so we ignore just one element, any one, and then this gives us a okay, so, and then we have, obviously, we have di dj equal dj minus 1 di if I is strictly less than j. Just easy verification. So in that sense, we have a, so this is the one part of the abstract simplicial complex. And then what we do is just the following. So we start from the standard 5 simplex. Let U be standard 5 simplex. And then we define two abstract simplicial complexes given by even faces of U or facets and the odd facets of U. So we have D0 U, D2U, D4 for U, and the Y is D1U, D3U, D5. So we have two abstract simplicial complexes. This is of dimension 4. because we are studying the facets of 5-dimensional simplex, so these guys are 4-dimensional. And then just think in terms of abstract simplicial complexes, and then you have this kind of thing. And then we define, so we pick up and this x and y such that so dx equal dy. So geometric realizations of x and y are homeomorphic to 4-ball. And so we can define the boundary of them. And this boundary, boundaries are identical in the sense of abstract simplicial complexes, and they are given by u minus ij. So it is given in terms of complements of 2 integers in that linearly ordered set, where I runs from among even faces, and j runs among the odd faces. So that's a set of 3-dimensional simplices of the boundary. So the boundary is 3-dimensional, so it's the boundary of 3-ball. 4-ball is a S3, and it is triangulated in terms of the data. And now what we do is the following. So fix gamma and map from G3 to the set of our indices. 3 means all 3-dimensional simplices, namely those guys. And consider associate for any alpha, for any 4-simplex P, and alpha from P3 to our index set, associate function, let me put this, q of P alpha, given by q alpha 0, alpha 2, alpha 4, alpha 1, alpha 3, where alpha I denotes just image of I facet of P. So these are 3-dimensional simplices. This is the 4-simplex, so the boundary are 3-dimensional. I color them by my index set, and this denotes just for this number which was entering into the identity. And now what is the claim is the following. Z3 is a set of 3-dimensional simplices of simplicial complex Z. And P3 is a set of 3-dimensional simplices of simplicial complex P. Okay, so. And now what I do, I consider, define now for any, okay, let me beta, gamma, delta, beta from x3 to 1, yeah? Define okay, let me just keep more economical, so define q of x gamma is fixed, so it will be product of q of di u comma gamma beta restricted to diu. Okay, that, with the same meaning as here. And here I sum over beta maps from x3 to index set, but with the restriction that beta restricted to z, which is the boundary of x, is gamma. Right? And yeah, and I, sorry. This is the product over I sitting in 0, 2, 4, and the sum over beta in, let me put it, index set power x3. And beta restricted to z is gamma. That's the thing, and likewise, q of y gamma, right? So the same formula, but the product over I running from 1, 3, 5, beta mapping the y3 to the same set with the same restriction because boundary is common. And then, so the proposition is the following, that qx gamma is equal to qy gamma for any gamma, if and only if we have a system of 3-3 Pachner relations. So that's a topological content of those algebraic systems. Okay, now let me just say how I solve it. And initially I have a solution which carries all necessary properties to end up with four-manifold invariance. Let me give, just remind you this solution, example of solution. So we take a G, a finite abelian group, chi of chi mapping A cross A to C by character. Then Q I J K L M given by chi of I K delta I minus L plus J delta of J minus M plus K is a solution.
By character, you mean just a couple of characters?
No, by character, which means that it is multiplicative with respect to both arguments. Is a solution of three Pachner relations. And instead of n, I'm enumerating my set of indices by group elements. Okay, so all these are group elements in it. So this is the solution, and if chi is non-degenerate, degenerate, then this gives a TQFT, TQFT in 4D, which means that we can realize all types of Pachner moves, and we can implement the complete four-dimensional symmetry of the theory. Yeah, but in principle, you can think about any finite abelian group, which is a product, maybe not canonically, of cyclic finite groups. Yeah, and in particular, just one cyclic finite group is okay. Okay, that's the example which I have since a long time, and today I would like just to show you that we can do more than that. And a group corresponds to a particular case of Hopf algebra, which is co-commutative for any group. But since we have an abelian group, so the underlying Hopf algebra is a bicommutative, finite bicommutative algebra, and I will show in a moment that we have a generalization of that class of solutions to any finite bicommutative Hopf algebra, but in characteristic 0, that corresponds to just to a finite abelian group, but in characteristic non-zero, you have examples, different examples, and even to the best of my knowledge, even the classification of finite bicommutative Hopf algebras in positive characteristic is widely open question.
So, you saying that is last comment?
I hope so. I hope so, but there is a problem, and the problem consists in the fact that I don't know any example of finite Hopf algebra in characteristic P of whose dimension would not be divisible by P. This example, yes. Yeah, they certainly do not detect smooth structure, but I know that they are more than signature and Euler characteristic. So I have examples. So presumably they, in the simply connected case, they correspond to Gaussian sums of the intersection form or the form manifold. But this is not proven. Yeah.
There are so-called D-graph written PQFTs, in this case associated with four-dimensional cocycle on a group.
But this cocycle is trivial, right? So you typically buy characters as trivial cocycles.
At least I would guess that any cocycle is a solution to a system of equations. And any finite group not necessarily that big.
But I don't know any more general form of that.
Four cocycle, just think. And the finite
This has to be seen. I don't know. I don't know. Maybe. Okay, now let me just state the result which generalizes this. So the result. Let B be finite dimensional by algebra. Or it could be Hopf, but maybe without antipode. And finite dimensional by algebra, and then P and Q B to be algebra by algebra endomorphisms such that P Q equal QP and P squared equal P, Q squared equal P. So these are some projections into a pair of subalgebras. And the image P on the PQ of B sits in the center of B. And omega B tensor B to ground field a pairing between B and B opposite and co-opposite. Then Q as a map defined in the following way: delta, tensor delta, tensor delta, composed with identity tensor P, tensor Q, tensor P, tensor Q, tensor identity in B, of course, delta, tensor, delta, tensor, delta, okay, I need more space, S, tensor identity in B, tensor identity in B, and product mu, tensor omega, tensor mu, that's a Q, which is a map from B, tensor B, tensor B, to B, tensor B, solves three Pachner relation with respect to some basis. Actually, any basis. I mean, we have 5 index objects, so if we have a map like this, if we choose a basis in B, then of course we will get a 5 index object of that map with respect to the basis. And the claim is that if we take that guy, then the matrix coefficients will solve our identity. And so here, no restriction whatsoever on the bialgebra. It can be non-commutative, non-commutative. S is a permutation. S, B, to be permutation, transposition. S of x, y equal y and x.
And what do you mean by pairing?
Huh?
What do you mean by pairing?
Yeah, by pairing, it means that, you know what is due Hopf algebra? Just in that sense. It means that the product in here is due to the product in here, and likewise for coproduct.
Do you require to be non-degenerate?
No, at this stage I don't, but according to that remark, so in which sense this generalizes that one? You just take B in particular, if B is bicommutative, P equal Q equal identity of B, and omega is equal chi, then we get this. And in particular, so to get a four-manifold invariance, you need chi to be non-generate, which implies that omega should be non-generate. And in particular, so the generalization of that example will be any bicommutative bialgebra, which is self-due by the form omega. Okay, I think I stopped here. Thank you.